I'll try to use that. Now, while Lynn addressed a little bit what we call the external packaging, the cartons, I will focus a bit more on what we call the internal packaging, and particularly with the effect of modified atmospheres and some other add-ons to optimize the management of temperature in the supply chain. So what are the types that we would say that are internal packaging materials? So we have then obviously the liners that goes into the cartons. We have the punnets, which are becoming more popular, which is cherry tomatoes, for instance. We have the filmy wraps and bags, like in salad mix, like that when shown. And we also have a combination sometimes of punnets and plus the wraps. So what would be the key benefits of having this internal packaging? They tend to reduce the damage to the product as they go from the farm to the retail. They tend to reduce, obviously, water loss and shriveling, which for vegetables in particular is a very important thing. As Lynn pointed out, they are very high water content, and the freshness is quite directly associated with the reduction of the water loss. They allow consumer packages and mixtures, such as the salad mixes that we see there. They allow added convenience, the options of which is becoming more popular as well, that the products that are ready to eat, that have been minimally processed or washed, and are ready to be consumed with minimum work at home. They are display ready, which is good in terms of less handling by consumers at the retail level. And also they can create modified atmospheres, which I'll talk in more details now. So modified atmospheres, basically, as the product respires, as Daryl mentioned, that it uses oxygen and releases carbon dioxide. So changing the concentrations of those two gases around the product can actually restrict the respiration and extend the storage life. How? By reducing ethylene production and the product sensitivity to it. As Daryl mentioned, that the ethylene is directly associated with the senescence of the product, the degradation of the product. It tends to reduce the yellowing by limiting the chlorophyll breakdown. That's very important, particularly for leaf vegetables in broccoli. And it tends to reduce the ripening and the color changing in fruit vegetables like tomatoes. It also reduces the breakdown due to rots and diseases, and also reduces softening, which is associated with the retention of the pectins that tends to hold the cell walls together. Just that graph, just to confirm that is the association between the respiration in here, and as it has the annoying thing that it darkens but as the respiration reduces, the storage life tends to increase. We can see several there, that's broccoli, sweet corn, just a combination of different vegetables in there, just to give us a visual illustration of how the relationship between the reduction of respiration and the extension of shelf life. So the most common modified atmosphere for vegetables is what we call the modified atmosphere of packaging, the MAP. Basically, the MAP uses the product respiration to change the storage atmosphere inside a package that has been sealed. The equilibrium atmosphere that develops in that over time will depend on the temperature, surprise, surprise. It will depend on the permeability of the film. It will depend also on the film area relative to the product weight. And the product respiration rate. As Daryl pointed out, no vegetables are created equal. So we can see here that the respiration rate from various groups of the vegetables or among vegetables vary quite a lot. It can go from very low for that group here to, let's say, less than 5 mLs per kilograms per hour to very high, for instance, for mushroom or sweet corn, which can go to higher than 60. So it can have like a tenfold increase depending on the vegetable. So, so how the map actually works. So initially, you have in this diagram using a bag with broccoli, for instance, you have the initial respiration rate of broccoli is greater than the gas permeation that goes through the film. So you've got a lot more CO2 released than NO2 consumed. With time, what happens is that as the oxygen reduces and the CO2 increases in the bag, that tends to restrict the respiration in the bag until the rate of the gases, the diffusion through the films sort of equates to the rate of the CO2 production and O2 consumption by the product. So it seems a simple product. However, there are risks that needs to be managed in there. Why? Because if the temperature rises above what would be the recommended temperature for that commodity, the increase in the product respiration is usually greater than the increase in permeability. So the product respires a lot faster inside the bag, for instance. And this means that the temperature is too high. That can cause the MAPs to become anaerobic if the oxygen falls too low. So what is the consequence? The product then may develop the undesirable flavor and off odors, like a fermented type of odor. And also plus it can allow the growth of dangerous bacteria, which can have serious, as Daryl pointed out, healthy issues. I recently bought some sweet corn and left in the fridge for way too long. And then when I tried to use it and I opened the bag, it was just unusable. That was my fault, not because it was sort of left there for too long. We can see here that the bottom line is that the modified atmosphere packaging is better suited to applications where the temperature can be closely controlled. So that the temperature control is critical. And this is particularly for products like I put those photos of the sweet corn, the rockets, and the mushrooms, for instance, because they are some of the products that had the highest respiration rate. So, and also there are products that they can be stored at 0 to 1 degree, very low temperatures. And if they are kept very, very long, the respiration rate then will be quite large. In terms of the permeability, they vary, of the films, they tend to vary quite widely depending on the type and the thickness of the plastic, the manufacturing technique, and the surface area. So some of the most common ones are what we call the integral films. They are permeable plastic films. They tend to be, in general, 3 to 4 times more permeable to the carbon dioxide than the oxygen. So the carbon dioxide goes through the barrier much quicker than the oxygen. And then we can also have what we call the microperforated films. In this case, there is the permeability for both the gases is a lot more even. Just to give an idea of the common polymers that are used in modified atmosphere packages, to give us an idea. So there's quite a range of them. And we can see here that what we call the oxygen transmission rate, which is an indication of their permeability, vary quite a lot. So we can see that it can go from 450 here on that measurement up to more than 1,000. So there's quite a lot of variation in there. So one of the trends that we can see also in films, as Lynn mentioned a little bit of that, is that there is an increasing focus on sustainability. So consumers are becoming more demanding more environmental friendly food packaging that can be made maybe from compostable or recyclable materials. This is particularly more I just put a few examples. These are examples of some vegetables like broccoli and pumpkin in South Africa using a hybrid polyethylene packaging. That's we call these products are usually made by these biopolymers or bio-based polymers that are gaining entrance into the markets internationally, and this will catch up in Australia. Just to give us an idea, just put that one in Spanish, just a recyclable punnet. There's a couple of key materials that seem to be quite promising. One is this PLA, is the polylactic acid, which it tends to, and the blends that are made by that. Just another example there with the recyclable pouch from Italy. And also the PHAs, which tends to have a very good properties and potential. Obviously, the cost tends to be the key in there. Usually, the PLA tends to cost maybe 50% more than the standard ones, and the PHAs maybe 2 to 3 times, at least from what I could check. Just to go into I just put this as an add-on because I thought that it was quite interesting. One of them is this 1-MCP, which is a synthetic plant growth regulator that blocks the action of the ethylene. And now in Australia, we have some sachets here on the right side that it can be added to the boxes and released. And this has been now commercially available in Australia. And I just saw that on the Vegetable Australia, which is the AusVeg magazine, one of the recent issues. They have the one grower in Western Australia that tested that in over 2,000 cartons by using the sachets added into the boxes to replace the top icing, which has a series of problems, cost, and environmental things as well. And apparently with some very good results. I just thought that was interesting because that was something that I would be very interested in maybe testing to see if there is, this was from Western Australia. He apparently shipped those boxes in Australia and overseas as well. But as usual with these technologies, there are always a lot of so this is just an example of some findings, some R&D work that DAF had, the impact of packaging on historic conditions of carrots that were destined to distant markets in the Middle East. We tested 3 different types of liners, including one that was that liner on the right, the MAP, which is biodegradable and also laser micro-perforated. We had some quite interesting results in terms of differences, showing that in terms of this is a percent of acceptable carrots, and we can see that the liners in the standard liner, which is the orange liner, had better results in terms of quality over time. There was this is another trial done with broccoli, which was part of an AusVeg funded project, which was led by Jody. Which was more simulating sea freight conditions and using what we call another type of atmosphere, which is not the modified atmosphere packaging, but the controlled atmosphere, which it can be used in containers, for instance. And again, we have quite interesting results, like the CA, the one here on the 2 had an extended shelf life compared to just the storage in air. Just to give an example. Maybe the take-home message would be that the MAP offers significant benefits in terms of improving quality and extending shelf life, and also in allowing consumer packages and added convenience. Given the complex and the risks associated with MAP to product quality and safety, effective and consistent temperature management is just vital. And then careful selection of materials and proper testing is required to ensure that the atmosphere that developed is inside is specifically beneficial to the product. And that's it. Thank you very much.